Hey class, last chapter, chapter 14, acids, bases, and salts. Okay, so a lot of this, or the very beginning, this is stuff that we already know. We already learned about one type of acid and base. This is the Arrhenius acid base. This is actually comes from Arrhenius theory. Again, the Arrhenius acid base theory states that the properties of an acidic solution, right, are due to the presence of H plus ions. So anything that generates H plus, right, ion in solution is an acid, and anything that is acidic, any type of solution that is acidic, has a high concentration of H plus. Remember that this bracket, this means concentration. Okay. Also, the properties of a basic solution are due to the presence of this hydroxide anion. So anything that dissociates, such as sodium hydroxide, in water to generate this hydroxide anion, that is considered a base. And a basic solution is a solution that has high concentrations of hydroxide anions. So of course, if you have a difference, even if you have hydroxide anions and this proton, H plus proton, in solution, right? If you have more hydroxide anions than protons, that solution is considered basic. We'll talk more about that in a little bit. So again, this is just completely review. HCl is considered an acid because when it dissociates in water, it dissociates into H plus and these chloride anions. But just to let you know, HCl is a covalent compound. But the thing is because we just learned the polarity of water is really compatible with the polarity of this linear compound. This is a polar bond because chloride is much more electronegative than hydrogen. So the chloride anion, or this is still, this is a covalent compound. There's no charges associated with it. But when we put it in water, the water, basically the solvent-solute interactions are stronger than the solute-solute or the solvent-solvent, and this dissociates into H plus and Cl minus. Likewise, I should actually also just go back and mention this really fast. So what do acids do essentially in solution? When we look at this H plus, right, does it float around just, if it's in water, right, remember this is all water, if this is just H plus, does it do anything to the water molecules, right? And the answer is yes. So even though acids, Arrhenius acids, form H plus in solution, what actually ends up happening is that this H plus proton, right, this cation, so to speak, it will actually protonate, and we call it protonating water. This is water right here. It protonates water to form this is H3O plus. Okay, so what really happens to acids in solution, they form H3O plus. Okay, because the Arrhenius acids dissociate into H plus and whatever respective anion, and then this H plus will protonate water to form H3O plus. This is because these H plus ions are highly reactive. So they bond to water molecules. Specifically, they're attracted to the slight negative charge on oxygen, okay? And there are no electrons associated with this proton, so even though oxygen has a full octet, it can take this full-on plus charge is attracted to the slight negative charge on oxygen, and it forms this H3O plus. This is called a hydronium ion. Just to let you know, also, chemists often use H plus and H3O plus interchangeably when they are referring to a hydronium ion. But this is actually what really forms in aqueous solutions with Arrhenius acids, hydronium ions. Review again, bases, right? They generate OH hydroxide. These are hydroxide. Right, these are hydroxide ions, and they don't. When hydroxide ions form in water through the dissociation of a base such as sodium hydroxide, these guys don't necessarily interact with H2O at all. Right, not like the protons do to form hydronium ions. Okay, so they just kind of float around. They don't necessarily interact or form any new species in water with water. So again, this is the same thing. I'm just going to go ahead and skip this. So here are some really common strong acids and strong bases. It's really important to understand what strong acid and strong base means, or specifically what we mean by strong. Strong means 100% dissociation in H2O. These are for Arrhenius acids and bases. So if it's a strong acid or a strong base, 100% dissociation in water. So hydrochloric acid, hydrobromic acid, hydroiodic acid right here, perchloric acid, nitric acid, also sulfuric acid. All right. Again, we know these are Arrhenius acids, all because of the presence of this H or proton. All of these guys dissociate in water to form H+. Specifically, and more specifically, I should say, H3O+. Here's some common strong bases, and again, these guys are always, these are very obvious that they're bases because they all have these hydroxide anions associated with them, right? And a strong acid or a strong base means 100% dissociation in water. So if I were to put 2 moles of lithium hydroxide in water, all 2 moles, every single one of those molecules will dissociate. So this is also, again, review under the Arrhenius acid definition, or the Arrhenius definition of acids and bases. They naturally combine to form water. All right, this is a neutralization reaction. Okay, so we have something like, again, sodium hydroxide plus hydrochloric acid, right, is going to, remember, sodium plus 1 cation, hydroxide minus 1 anion. Then we have our H plus and Cl minus, right? The cation from the first is going to react with the anion from the second, and we're going to form NaCl, sodium chloride. This guy is soluble, so this is our soluble salt. And then we have OH and H+. Those guys are going to form water, liquid. And long story short, because this guy dissociates, and then if I wanted to do my net, all right, which is our net ionic equation right here, okay? Always forms, so the protons and the hydroxide anions combine to neutralize and form water. Again, same thing. These are neutralization reactions. This is what I just drew before. And here's another acid-base reaction right here if you want to take a look at it. So this leads us to titrations. This is something that we talked about in lab this week. Titration is the reaction of a substance in solution with a known concentration, specifically molarity, with another substance in solution with an unknown concentration. It is an analytical technique. So you can use the coefficients in acid-base reactions from the balanced chemical equation to determine the moles of unknown from moles of unknown. Moles of unknown from the moles of known. And we know that the, well, here, I'll skip forward. So important things about titrations, you have to have some type of indicator. In our lab this week, we used a color indicator, phenolphthalein. It is clear in acidic solutions and it is pink in basic solutions. We also sometimes have to standardize certain things. We had to standardize our NaOH solution before we could even begin titrating our HCl solution. And then the other thing is equivalence point, the point in the titration when the number of moles of base equal the number of moles of acid in solution. Okay, this is different from the end point. The end point is where the color indicator changes. Oops. Changes color. The endpoint in, for example, when we did the acid-base titration with HCl and sodium hydroxide, the endpoint is when there's a little, remember the color indicator, phenolphthalein, has to be, in order for it to be pink, there has to be a presence of hydroxide anions in solution. So the solution has to be a little bit basic. So the equivalence point comes first. That's when the moles of acid equal the moles of base. And then we have to go a little bit further, right? Add a little bit more sodium hydroxide to a solution so the OH molecules, right, the hydroxide anions can interact with the phenolphthalein to turn the color, to turn from clear to colorless. So the endpoint is a little bit after the equivalence point. So we can do some stoichiometry with our acid-base solutions, considering what molarity and all that stuff. So what volume of a 0.5223 molar solution of sodium hydroxide is required to completely react with 3.457 grams of oxalic acid? Okay, so this is exactly like our lab from before. What we're going to do first is we start off with, we know that we have a concentration of, we have a known concentration of sodium hydroxide. We also know that 2 moles of sodium hydroxide react with 1 mole of oxalic acid, which is H2C2O4, to give us Na2C2O4 plus plus water, obviously, right? So since we know that oxalic acid and sodium hydroxide react in a 2-to-1 ratio, and we know the concentration of sodium hydroxide, we can we can first figure out how many moles of oxalic acid we have. I gave you the molar mass, so we're going to first convert 3.47 oxalic acid to moles using the molar mass, 126.07 grams per 1 mole. And that would give us moles of oxalic acid. And then we know that for every 1 mole of oxalic acid, we need 2 moles of sodium hydroxide to react. So that's 1 mole. Okay, so that's going to give us moles of sodium hydroxide that we need to neutralize the moles of oxalic acid. And of course, I can never, ever, ever, I don't know why, I'll never learn, will I? I'm looking for, oh, there's my calculator. So I'm going to go ahead and plug this in my calculator, and what this is going to give me, again, this is going to give me the number of moles of sodium hydroxide needed to neutralize, this guy right here, 3.45 grams of oxalic acid. So 3.457 grams of oxalic acid, 1 over 126.07, multiplied by 2. And that's going to give us, 0.0 this is mole NaOH. Okay. Now we are working with 4 sig figs, so that's 1, 2, 3, 4. All right. So really, I'm just going to go ahead and drop that. That's fine. All right. Now what we do, since we have the concentration of the sodium hydroxide solution, we can just take this 0.05484 mole NaOH and multiply that by the inverse of the molarity. Because remember, molarity is moles per liter, so it's 0.5223 mole per 1 liter, right? And that will give us, so moles cancel, answers left in liters, that will give us the volume in liters needed to neutralize 0.5223. So that's going to give us 0.1050 liters of this solution, okay, is needed to neutralize this much oxalic acid. We'll do this one in lecture. So now that we know we can use stoichiometry with our acid-base reactions, let's compare another type of, we know about Arrhenius acids, let's talk about this new type of acid that I'm going to introduce to you called Bronsted-Lowry acids. All right, so there's a new type of acid, an acid base that we're learning about. So again, we know that Arrhenius acids, well, I'll just go ahead and say Arrhenius acids cannot explain why some substances act as a base even though they do not contain OH. Okay, so basically, long story short, is that Arrhenius acids and bases are only a certain kind of acid and base. There are other kinds. The other kinds of acids and bases are Bronsted-Lowry acids and bases. This encompasses a wider range of acid-base phenomena, and basically what this does is it expands into non-aqueous solvents, right? Arrhenius acids and bases were in always aqueous solutions. So in the Bronsted-Lowry theory of acids and bases, an acid is a proton donor, okay? So it still generates H+. But the difference is a base is a proton acceptor. So it's anything that gets protonated by an acid. So technically, water, pure water, when it interacts with, let's say, HCl, right, it's going to form, we already know, this H3O+, okay? So in this situation right here, we have an acid that generates H+, and technically water is a base because it accepted the hydronium ion, or it accepted the proton to form a hydronium ion. So here, this would be, even though this is in water, right? This is water. This is an aqueous solution of water. You can see how Bronsted-Lowry acid bases are more encompassing, right? This isn't a base because it generates OH- in solution. It's a base because it accepts the proton from the acid. So here it is right here. According to this definition, HCl is a Bronsted-Lowry acid because in solution it donates a proton to water, and this definition is more clearly accounts for what happens to H+ ion from an acid. It associates with water to form the hydronium ion. So again, so Bronsted-Lowry theory of acids and bases, we have an acid right here. Okay, this is an acid. And we know it's an acid because it generates H+, it dissociates in water to generate H+ and NO3-. And again, because it's in water, it's going to protonate water to form our hydronium ion. We should put brackets around it, but that's okay. Okay, so it's going to form this guy right here. So water, again, acts as a base, specifically a Bronston-Lowry base. So now let's look at this reaction right here. So here we have ammonia, right? NH3 plus H2O. Now here's what happens. This can happen a lot, all right? Ammonia is going to act as a base, because let's look what happened. Let's say you have no idea what's going on in this reaction, and I just gave you this equation right here, and I asked you to tell me which is the acid and which is the base. Well, what you have to do is you have to follow the story. You're going to have to look before and after. Here we have ammonia. If we go to the product side, what happened to ammonia? It became I'll draw this a little bit better. What happened to ammonia? It became ammonium, right? It became NH4. It gained a proton. It gained H+. And with water started off as water here, and then what happened to water? It lost a proton. So in this situation, water is the acid because it donated a proton, right? It lost it at the end. And ammonia is the base because it accepted the proton. Okay? So this is a different example, right? Before we showed you where water acted as an acid. Now it's acting as a base. I'm sorry. Before we had water acting as a base, now it's acting as an acid. So this is what this means, amphoteric. All right, so a species that can behave as either an acid or a base, and that would be water. And again, here in this example, water started off as water and it ended up as H3O+, so it acted as a proton acceptor. A proton acceptor is a base. But then we look at this example right here. We start off with water, and then what happened to water? It lost a proton, so it acted as an acid in this situation. Okay, so water is an acid in one case and a base in another, and that is totally normal because that is what water does. This is the same thing again, but the one take-home message that I want want you guys to understand is I'm going to introduce this concept of conjugate acid and conjugate base. So if we look at the reaction between HCl and water, okay, we can see HCl. We know HCl is an acid. Okay, it's a strong acid, but let's follow it through. HCl starts off as an acid. And ends up as a chloride anion, all right? In some situations, right, this chloride anion can accept a proton. So we're going to call this is called a conjugate base. And I have it written right here. Conjugate base. So anything that starts off as an acid ends up forming, this thing called a conjugate base. Okay. Water started off as a base. And what did it generate? It by accepting a proton, it generated a conjugate, because I have no room, I'm going to abbreviate. It generated a conjugate acid. We call this a conjugate acid because H3O+ can, under certain circumstances, also act as an acid, all right? But here's the thing with these acid-base reactions. They always occur together, and they always occur in pairs. So an acid starts off as an acid. When it gives up its proton, it becomes a conjugate base. A base always starts off as a base, and then once it accepts a proton, it becomes a conjugate acid. Here's another example. In the reaction between ammonia and H2O, H2O is the proton donor, right? It's the acid. And if we follow it through, it's the proton donor. So it loses a proton, and it forms a hydroxide anion. That is the conjugate base of water when it acts as an acid. Ammonia starts off as a base, and once it reacts with water, accepts the proton, it now becomes a conjugate acid. This extra proton that it gained can be given up, right? That's why, and actually, because you see these double-headed arrows, this reaction can go back and forth, okay? So conjugate acid-base pairs essentially all differ from, they all differ by a proton, so to speak. So a base is a proton acceptor, right? A base will go over and form, once it accepts a proton, it forms its conjugate acid. An acid is a proton donor. Once it gives up its proton, it becomes a conjugate base. This is where the conjugate acid-base pair comes from. Any two substances related to each other by the transfer of a proton is considered a conjugate acid-base pair. So again, over here we have ammonia, right? Ammonia acts as a base. When we add a proton, it becomes NH4. That's its conjugate acid. This can act as an acid in certain situations. But either way, this is a conjugate acid-base pair. Water. If it's put in a situation where it's going to give up a proton, or a proton is removed from it, right? It will act as an acid, and once it loses that proton, it becomes its conjugate. It forms its conjugate base. So again, this is the conjugate acid-base pair. Again, two species that differ by one proton. All right. So in an acid-base reaction, again, bases always accept protons and become a conjugate acid. So water, in this situation, we have hydrochloric acid and water. Water is going to act as the base. So we follow the line over. It starts off as a base, and then once it accepts a proton, it forms its conjugate acid. And here we have H2SO4. It acts as an acid, and once it gives up one proton, right, even two, but this will stick with one. Once it gives up one proton, it's going to form its conjugate base. All right. So bases accept protons and become conjugate acids. Acids donate protons and become conjugate bases. We have been over this several times, so I'm going to skip this. So here we have a certain base, right? This is carbonate. It's bicarbonate. Sorry, it's bicarbonate. And we have water. All right. So let's say we don't know what these are. So I'm just going to actually go ahead and do this. You're given a reaction that looks like this. Okay. And you have to tell me which is the acid, the base, the conjugate acid, and the conjugate base. The way that I would do this is I would follow the before and after. So we look at water. Water starts off as water, and then if we follow this line, it lost a proton. So since it lost a proton, water started off as an acid and generated its conjugate base. So I'll put lost. Likewise, if we look at bicarbonate, we're going to say, all right, well, it starts off as this, and then if we follow this guy, the line, if the line is not there, I would just draw it. I would draw it if I were you. Oops. And then what happened? It gained a proton. And of course, you know that it gained a proton because water lost it, so it had to go somewhere. It gained a proton. So going back and evaluating the reactant, since it gained a proton, it started off as a base, and once it gained the proton, it formed its conjugate acid. So summary of these acid-base theories really quickly. Arrhenius, right? Arrhenius acids and bases. Arrhenius acids form H plus, and so H plus are acids and OH minus are bases. Okay, if the concentration of H plus is greater than OH minus, then it's considered acidic, the solution. And if the solution is greater in concentration of OH minus than it is in H plus, it's considered basic. Okay. Bronston-Lowry acid-base theory. The acid is a proton donor. Okay. The base is the proton acceptor. We form acid-base pairs with this situation, conjugate acid-base pairs with Bronston-Lowry acids and bases, and water can act as both an acid and a base. Okay. And I'm going to talk about one more thing and then we'll stop here, or we'll stop right after this. So I just mentioned that water can act as either an acid or a base, and that's true even with itself. Okay? So in pure water, where there's nothing else in there, water acts as an acid and a base with itself. This process is called autoionization or self-ionization of water. It's where two water molecules interact with each other, and because of essentially the polarity of water, all these water molecules are in close contact with each other, they're interacting with each other, and basically, and there's so many of them, eventually at one point in time, one water molecule will donate a proton and form a conjugate base, and the other molecule will accept the proton and become a conjugate acid. Okay, so this is the autoionization of water. It is water by itself acting as both a base and an acid. Okay, this double-headed arrow again means that this reaction can go back and forth. It's reversible, all that kind of stuff. And this is what is constantly happening in pure water, right? A proton is constantly getting transferred back and forth, back and forth, back and forth. This is the autoionization or self-ionization of water. So the self-ionization of water, this is essentially the reaction right here. Two water molecules interact in such a way where one forms a hydronium ion, and then because the hydronium ion is formed, there's also a corresponding hydroxide ion, right? Even though it's a tiny amount, there's an equation to relate the concentration of hydronium and hydroxide ions. This is called Kw. This is a proportionality constant. Remember, these brackets mean molarity of or concentration of. Specifically, it means concentration of, but most of the time we look specifically at the specific concentration is molarity. So at room temperature, Kw is equal to 1.0 times 10 to the negative 14. Okay, so that means that in pure water at room temperature, the concentration of H3O plus ions is equal to the concentration of OH minus ions, and that is equal to 1.00 times 10 to the negative 7 molar. So let's take a look at that. 1.00 negative 7. So it's 1, 2, 3, 4, 5, 6, 7. So this is a really small concentration. All right, let's delete that right there. So that's how many zeros are found. So this is very small, okay? But this is, again, this is called Kw. So Kw is equal to, at room temperature, it's equal to 1.0 times 10 to the negative 7 molar, and that is when H3O plus is equal to OH minus. We are going to stop here and we will pick up where we left off and we'll talk about solutions next.